Hi. Today we're going to be going over our um, the math worksheet that I sent out in preparation for the math exam you guys have Tuesday. Just some notes about the exam in general. It's really conversion heavy, so you're going to have problems where you're going from fluid ounces into like milligrams per ml, and then you're going to have to do the math because we're only trying to do math in metric, and then you're going to have to go back to fluid ounces. It's kind of like a back and forth game, but you got to do what you got to do. So I have listed out all the conversions that are really important to know. I only use 1 ounce is equal to 30 grams and 1 fluid ounce is equal to 30 milliliters, just because those are really easy, and I think that it makes it harder to mess up because you might substitute out one when you meant to do the other. So I only use the 30. Um, Knowing that a gallon is 128 fluid ounces, that'll in a quart, no quart, like know what a quart is. It's 1/4 of a gallon. Um, so like 32 ounces, 32 fluid ounces. Um, so gallon being 128 fluid ounces, and then you can just multiply it by 30. That'll give you how many mLs are in a gallon. I don't trust myself to properly remember which one of the values is what. Like a gallon is actually like 36, whatever. I just do the 128 times 30 because again, that it just helps me know that I'm not messing up. So things like that, it's kind of like putting guardrails up for yourself just to make sure that you don't accidentally mess up on things. Know the caloric conversions. I'm not saying it's on there, but I think you would benefit from knowing the caloric conversions. Um, I did not know those. Whatever. So another thing that you might have interest in knowing is um, body surface area. So it's meters squared, and this is on that sheet, and it'll be given as a PDF, and then it'll also be in our Google Drive as like a Google Doc, so you can make a copy of it yourself and like mess around with the values. So meters squared is equal to the square root of centimeters times kilograms over 3,600. But in imperial measurements, it's inches times height over 3131. And you take the square root of that. 3131. 3131. It's important to know. Specific gravity, that also might show up in various confusing ways. Cockcroft-Gault, I have no recollection of that being on the exam, and it wasn't on any of the worksheets, and it wasn't on any of her slides, so I wouldn't really worry about it. MEQs, take a wild guess if they show up or not. mOsms, take a wild guess if they show up. And millimoles, I don't remember them showing up actually. So going into the actual problems, I'm going to address the acronym first. So D for directions. I for initial value. F for final value. No. No. That was in my like original version, but it like didn't quite line up. So L for last value. F for formula. And then formula. Finally, D for decimals. And I really want to emphasize the decimals part because she's like a watchdog on those decimals. And there are going to be questions where the decimals are going to be really iffy, and you're going to be like, whoa, where did those decimals really come from? Let me think about this. So, just important to keep in mind. So, I'm going to leave this in this corner as we go through, and that's just something that you can keep in your mind, write it on the page. I think you should write it on the page. That'd be really funny. Um, maybe don't. I don't know if she would find it funny. Anyway, um, so directions, initial, last, formula, decimals. That's a good way that I walk through the equations and the problems just to make sure that do I have everything that I actually need? Because she also likes adding red herrings in the questions, like things that have nothing to do with the actual solution and how you get there. They're just erroneous values that show up and do nothing. So, yeah, that's fun. Anyway, so to start with allegation, a patient comes in and orders cracked ice cream for the cracks he has on his ass crack, which is slang for anal fissures. The compound calls for 5% pentoxifylline, which improves blood circulation, and you have stock of 20 and 1% creams, and nifedipine, which is 0.05%, and you have 100% pure nifedipine and a drugless vehicle. How many milligrams of the 20% cream do you need to use to get 5 of 5%, 5 grams of 5%? And how many ounces of the inert vehicle would you need to make 5 grams of 0.5%? So our total value is going to be 10 grams. And so we read through our directions. D. Let's look at our initial values. So our initial values here are, so let's just do the first part. The milligrams of 20% needed to get 5% of pentoxifylline, 5 grams of 5%, excuse me. So we have 20% stock, 1% stock, and our last value that we're kind of looking for is milligrams of that 20. So for this, we're going to use the I'm going to use the tic-tac-toe method, and shout out to Carly M for doing the algebraic method in the key. I have no idea how to do those. I only do the tic-tac-toe method. I don't like math. I don't know why I'm doing this. Let's do it. So again, thank you, Carly. And just working through those problems as the tic-tac-toe method. Yeah, you're still in view here. So we have our 0.2, our 0.01, our goal. So I think of this as like a pseudo last value is 0.05 because that is the goal concentration that we're going for. So going up through this way, subtracting this way, we get 0.04. Going down this way, we get 0.15. 0.15. And so these two are in a ratio to one another. In that ratio, this is how much of the 20% you need, and this is how much of the 0.5% or 0.1% or whatever, 1% you need. So this is how much of the 20%, and this is how much of the 1% you need. So what I like to do for these is I take the total of these two together, which is 0.19, divided by the amount of our goal, or what we're trying to find, which is this guy. So we run that across, we get 0.04 because it's 4%, or yeah, that we're looking for. That is not a calculator. This is also good calculator practice. Know your calculators. They have store and recall values on there, so it makes rounding a bit easier. So that's 0.04 divided by 0.19. And if you want to do this in percents instead of like the actual minute values, so if you did like 20 and 5 and 1 instead, that would be completely okay. I just think about problems like this on the minute level. That's just the way that I work through them. So that's 0.19. So 0.04 divided by 0.19. In other words, that would be 4 divided by 19. Either way, the amount that you're going to get is going to be the same. It's going to be around equals 0.21. And because we don't round, it's going to be 0.215 to whatever. And then again, this is just a ratio. This is like a converting amount. This is the ratio of 0.2 that we need in order to achieve our full 5 grams. So we take our ratio times our final 5 grams times 5 gets us 1.05 grams of 20%. If I'm right, yeah, 1.053. So she rounded to 2 decimals because it's 1.0536. And on the exam, she would specify round to this many decimal places. Oh, fear. From what I remember, most of them are going to be rounding to 2. But, yeah. Just the final D part, the decimals, that's something that I go through many, many times. So I went through the entire exam and then I looped back and I rechecked all of my decimals. So this is something that you just kind of like star for at the end. And so you do it once, decimals, and then you go back through and check all of your answers again, decimals. Do the decimals. That recheck takes maybe 5 minutes. And yeah, a lot of people weren't able to finish on time, but I feel like a lot of that came from just the sheer amount of conversions that we had to do. And also for the conversions, doing like a Quizlet would be really, really helpful. And just like inputting a bunch of random values and then translating out, that would just be like, it would pretty much just be multiple like rounds after rounds after rounds of conversions, and that would really train you up. Anyway, back to the regularly scheduled program. So 1.05 of the 20, so 1.05 grams of 20% cream gets us the amount of 20% we need, because that is our last value. So circle that. Congrats, we did it. Moving on to the nifedipine portion, I am going to leave most of this up, or at least the tic-tac-toe part up, just for like simplicity, so I don't have to redraw it. And it's asking for this smaller corner now. How much of this smaller corner? So that's our last value. How much of this smaller corner do we need to get to our 5 grams of 0.05 nifedipine? So we have 0, because that drugless vehicle, again, going back to our initial values, that drugless vehicle has a concentration of 0. And that pure powder has a concentration of 1. And our goal is 0.005. So, and if you were doing this in whole numbers, you would use 100 and 0 and 0.5. That's just like something to think about if you're doing the whole numbers. So going down this way, you get 0.995. Going up this way, you get 0.005. And when you're going like this, and it might make a negative number, it doesn't really make a negative number. It's just like an absolute value thing because it's a ratio. So cross like that, add these two together, you get 1, and looking for this value. That's 0.995 divided by 1 equals 0.995 times our 5 grams. 5 times 0.995, 497.5 equal to 4.975. And then again, if this were, you see that? Yeah, you can see that. If this were an exam, she would say round to 2 decimal places. And so you'd make it 4.98. And then that would be the problem. And you just put that into ExamSoft. So that's allegation. And again, look through Carly's notes on how to do the algebra version. I'm not a great resource for the algebra because I am just not effective at it. Jesus. So our next problem set is going to require a little bit of a lecture. So if you need to, please pause your viewer because this is going to be a little bit dense. So milliequivalence is a measurement of ions in solution. It's kind of like an amount of electrolytes or a concentration of electrolytes. If its concentration is going to be MEQs per liter. And it's measured in, I really need to wipe that off better, whatever. It's measured in, or it's determined by the electrolytes. So ME, underline that, Q is equal to the electric charge. It says change, but whatever. So let's think of an example. K3 citrate. Let's split it up. These potassiums have a charge of +1. The citrate has a charge of -3. Because of how this potassium works, since there's 3 of them bound to one citrate, it still has a total electric charge of 3. And since there's just this one citrate, so it's that times that. Not, okay. That times the charge. And so there's one citrate times a charge of -3, it's just 3. So if you were doing, what is the MEQ of 150 milligram citrate, it would be MEQ, that's a G, Q is equal to 150 times 3 over whatever the molecular weight is of citrate. I can't remember the molecular weight of citrate off the top of my head. Or potassium citrate. Because the molecular weight is the entire molecule, not just one of the ions that you're looking at. So that, yeah. An easier way, in the way that I think about it, is what is the largest charge in the compound that you're dissolving. So the largest charge is citrate with a -3. It's going to be the -3. If you're looking at something like, let's think, potash, K2CO3. So the largest charge, K2, these have a charge of +1. This CO3, this carbonate, has a charge of -2. So the valence is just going to be, when I say charge, I'm also talking about valence. I'm sorry, I should have clarified that. that is going to be 2. So it would be 3 or 2. Because those are the largest charges and everything else is a small charge compared to it. And so the potassium is acting more like a balancer just to make sure that it stays even with that -3 or that -2, depending on which one you're looking at. Going on to the questions, let me clear off my board really quick. Her questions for MEQs are going to be really involved, and they're not going to be as straightforward as the ones I give you now. She's going to be incorporating other factors into it to kind of like beef up the problem. So she'll bring in, I'll leave that there. Electric charge. She'll bring in like other large factors. She'll bring in like a dose question where she's going to ask like, I don't know, this might have been on one of the worksheets. It's like how many MEQs is a patient, or how many milligrams is a patient getting per day if they're on a 15 MEQ per liter thing and they get like 4 liters a day, so something like that. But just to get a more basic understanding of it, because MEQs, milliequivalents, can be really confusing. Oh, also she likes to make you do your own addition for molecular weights. So I throw a bunch of those in. How many milligrams of potassium chloride are there in 2 liters of 15 MEQ per liter? Okay, cool. So that is the directions. Our starting values are potassium chloride with a weight of 74. So they have a weight of 74 is equal to 2 MEQ per liter. No, 15. Backwards. 15. This is why you highlight and group things together. If you highlight and group them together in a way that like makes sense to you, you're not going to have that kind of like mess up where it gets like tripped up. Times 2 liters is equal to our milligrams, which is our last value that we're looking for, times valence. Now, take a quick second. What is the largest charge in this solution? They're the same. They're a positive one and a negative one. You don't add them together. You don't multiply them together. They're just a positive one and a negative one. So that's times 1. Shorten this up. And would you look at that, we have our formula. I kind of jumped the gun on the formula part. But yeah, once you kind of know the values that you're looking for, the formula part is, yeah, it comes. So 15 MEQs per liter times 2 liters, you have a total of 30 MEQ. Milliequivalents equals that. Let's do X instead of milligrams just because X is easier for me to work with. You multiply by both sides, so be going like that. So 30 times 74 is 74, 2,220. 2,220 is equal to X times 1. So, and since we know that X is milligrams, milligrams, and also that's an important part. When you're doing MEQ, it's milligrams over molecular weight. It's not like when we're doing weight per volume calculations and it's like grams over milliliters. It's just milligrams, like straight out of the start. So 220 is equal to your milligrams. So there you go. Sorry, I gotta get back down. How many, and this is the next question. How many MEQs, milliequivalents per liter of sodium, are there if you dissolve 1.5 grams of sodium in 5 liters of fluid? Let's just do water. I don't know why I said fluid. It must have been like after renal. MEQs per liter again. So, it's starting to smell like rubbing alcohol in here. Whatever. So MEQs per liter. You may or may not end up seeing questions that involve MEQs per liter. So we're looking at, oh, so that's the goal. Okay. So we're looking for, well, let's go up here. MEQ is equal to, looking at our initial values, 15.5 grams of sodium times 1,000, 23 for molecular weight. Bold. So I'm bolding this as I go through this question, so I can stay. That's why I like highlighting. Anyway, so our MEQ equation, like I said, only works if it's in milligrams. So we first have to multiply our 15.5 grams of sodium by 1,000. So that'd be 15,500. 15,500. And our valence for sodium is just 1. So times 1 over our molecular weight. Now, normally you would take the weight of sodium plus the weight of chloride, but this time the question is only asking for how many milliequivalents per liter of sodium are there. It's not asking for anything about chloride. So you do that over 23, and that will give you, un momento, divided by 23, 6,000, 600. So MEQ equal to 673.9. But this isn't the end, because we have 5 liters of fluid, and our goal, our last value that we're trying to get to, is milliequivalents per liter. So we need to take our 763.9, and you can just do this, what the number you get divided by 5, and you get 134.78. And I'm just going to do 2 decimal places for all of these just because it's what she's going to ask. Yeah, MEQs and milliequivalents per liter. Final milliequivalent question. 10 fluid ounce vial, 1.5, 10 fluid ounce, bold. 1.5% solution. Okay, this is one that is very similar to one that she'll do on the actual exam. So you have, no, whatever, 10 fluid ounces. And I would just multiply that by 30. So 10 by 30 is 300 ml. How many MEQ are in this file? Okay. So final value, looking for MEQ. 300 ml. And to get to MEQ, we first need to be able to fill out the equation which is milligrams times valence over molecular weight. And this is one that I think, yeah, we're going to have to do our own. 16 times 3 plus 12 plus 40. 12 plus 40 is 100. That doesn't sound right. That's 40 plus 12. Okay, 1 second. Here. All right, that looks right. So I don't know why I think that was like dead wrong. Anyway, 10-ounce vial. So our molecular weight is 100. Our valence, what is the largest molecule in the solution? Calcium and carbonate both have charges of -2. So we're looking at 2. And now we need to find the milligrams. So 300 ml from 10 fluid ounces times 30 ml per flaz. 300 ml times 0.015. Nope, 0.015. Because, yeah. So 300. And this is also the same as saying times 1.5 divided by 100 ml, just for like simplicity, because I know that that's like the way that we've been taught. Times 4.5. Now, what units is our weight per volume in? I said it a minute ago. It's in grams. So that's 4.5 grams, which means we need times 1,000, 4,500, 4,500. And then from here we can finally do our equation. So that times 1,000 times 2 divided by 100 is 90. 90 MEQ. So that is one that's fairly loyal to how she'll do the exam. Oh boy, osms. So milliosmoles are in kind of the same boat as milliequivalents, where they can be really, they're kind of difficult to differentiate from one another. So for milliequivalents, we're looking at the electric charge. E, electric. With milliosmoles, I have another thing for this. With milliosmoles, so I'm just going to leave it as equals E for like electric charge. For milliosmoles, mOsm is equal to number of species. So it's kind of like how many separate molecules are floating around in our solution. So we have tank of water. How many particles are in here bumping around against one another? Like how many are just like kind of bumbling around? That is the way that I think of it. So number of species with the O is equal to osmoles, milliosmoles, I should say. Again, working through the Delft the equation. If you dissolved 150 grams of potash into enough water to make 120 milliliters, what would you expect the mOsms to be, millosmoles to be? So let's break down what are our initial values, 150 in enough water to make 120. That's our volume. And we have molecular weight. I actually gave us the molecular weight this time. Sweet. So 150 grams. Let me get rid of this. And our millosmol equation is equals to milligrams. And again, it's milligrams for this one. It's not grams like it is for our weight for volume, times number of species. Again, there's that O, species, divided by molecular weight. So we have milligrams, we have 150 grams, so we need to multiply that by 1,000. So we have 1,000, 150,000, Jesus, times number of species. If you put K2CO3, how many species would there be floating around? And it potash completely dissolves in water. So that would be 3 species. 3. That'd be times 3 divided by a molecular weight of 138. 138. That would be 450,000. 450,000 divided by 138. Big number. Into cool. Yeah, that tracks. So final count is 3,260.87 milliosmoles. Now you might be thinking, what about the 120 milliliters? That is an example of one of the red herrings that she would throw in. If I said per liter, then you would do like that many divided by 120 is equal to X per liter. And you'd find out through the algebra method there. I know that out. I need to stop dropping that. I know that algebra method. So this is also, this next question, so we're moving on to the next, is also, I think, very helpful. So 2 gallons Epsom salt, magnesium, Epsom salt is magnesium sulfate. I can't remember the actual name, but it's MgSO4. And it's a hydrated salt. So hydrated salts have an associated water count that are present before it's dissolved. And you'll see it denoted as MgSO4 plus or multiplied by 7H2O, or just equation 1 multiplied by however many waters it's associated with. I'm going to put that up there. So, yeah, I'm not adding that molecular weight together, thank God. 2 gallons of Epsom salt, bath with 1 pound, 4 ounces of Epsom salt. What is the milliosmoles per liter of this solution? I feel like this is also a really honest recreation of the kind of questions she'll see. And also, this will be the last part for this video. I'm going to do parts per million, specific gravity, nutrition, and isotonicity in the next one. And then the final one will be miscellaneous math problems. So, final question for this video, and then get a snack, run a lap, something. So 2 gallons is, oh, this one's fun. So we have the initial value. This is not the right marker. Where is my actual marker? There we go. Okay. We have 2 gallons. This one is also kind of getting tired. Gallons. And each is 128 fluid ounces. Flaws per gallon times 30 milliliters per flaws. I'm just getting it into liters because the final, this is me kind of looking at the last value. Our last value is milliosmoles per liter. So times 1 liter per 1,000 ml. So then you just run through that entire stoichiometry, or you can just know how many liters there are in a gallon. I don't do that. I don't trust myself to remember that correctly. So 2 times 128 times 30 equals that. That is not right. 2 times 128 times 30 divided by 1,000. 7.68. That sounds right. Equal to 7.68 liters. 1 pound, 4 ounces of Epsom salt. So each pound is also a good way to remember pounds and make sure you're right. The LB kind of looks like a 16. So 16 ounces in a pound. LB, 16, they look really similar. So that's 16 ounces plus 4 ounces equals 20 OZ multiplied by conversion factor of 30 grams per ounce. So 20 times 30, can't do math, like 600, I think. Yeah, 600. 100 grams. And again, to use our milliosmol equations, we need that 600 to be in milligrams. So you multiply that by 1,000, get 600,000. And now we can start looking at the rest of the equation, because we have the 2 pieces that we need to kind of convert it into its final form. So 2 gallons of Epsom salt and 1 pound, 4 ounces. Okay, cool. So molecular weight, 246. Now, for number of species, this is where things can be a little bit confusing. The water counts towards your molecular weight. It does. So the water counts towards the molecular weight, but it does not count towards the number of species. I don't know why. It just doesn't. Because when you're pouring something into water, I guess that hydrated salt just becomes part of the water. I don't know. So MgSO4, that's the actual Epsom salt part. That just has 2 species, the magnesium and the SO4. So that's times 2. That's 600,000 times 2 is 1.2 million divided by 246 molecular weight gets us milliosmol count of 4,878.0487. This is going to be one of those where you just like keep it in your cap. Never mind, I got rid of it. And then it was per liter. Divide that by 7.68. 6,351.62 milliosmoles per liter. Okay, so that's it for this one. I just want to get through the MEQs and mOsms just because those can be really dense, and it's worth just letting that sit and letting yourself think about that. Maybe running through some of Sanoski's worksheets with trying to think about, okay, this is how many molecules are in that solution and how many are in there per liter, even if it might be lower than a liter, even if it might be higher than a liter. All right, so I will see you all back shortly probably shortly. Maybe you want to like take a walk. Parts per million, specific gravity, and nutrition. Maybe isotonicity. I don't know. It'll depend on how fast I go.